Chemistry 30, Redox Reactions, Lesson 2. Determining spontaneity from the data table and balancing half reactions. In redox reactions, we always have an exchange of electrons. If both reactants are looking to gain electrons, no reaction will occur. If both reactants are electronically satisfied, meaning they are not looking for electrons, no reaction will occur. In order for a reaction to occur, one reactant must be looking for an electron and the other reactant must be in a position to lose an electron. But that doesn't automatically mean a reaction will take place. An exchange of electrons only occurs if the reactant seeking electrons is stronger than the reactant that could give up the electron. Silver ions can strip electrons from aluminum atoms. We call this a spontaneous reaction. But aluminum ions cannot strip electrons from silver atoms. We say this is not a spontaneous reaction, meaning if put together, there would not be a reaction. So why is this? To understand, let's look at our standard reduction potential table that is on our green data sheet. So we said silver ions can strip electrons from aluminum atoms. If I look on my standard reduction potential table, this is just like the one you have, but so that we could see these lines, I've shortened the table up by taking out some of the reactions that we won't be concerned with in the examples here. So I look for Ag+, there it is, and I look for Al, oh, there it is, and they line up this way, which means they're lining up in a position of will. Ag+ will reduce when Al is oxidized. So this reaction would take place. If I look at Al3+, there it is, and I look at silver, there it is, it lines up in this direction. And that is a won't. Won't oxidize, won't reduce in this position. That means that Ag will not give up electrons to aluminum ion because silver is stronger. Silver wants the electrons more. So to repeat that one more time, in order for a reaction to take place, you must have a reactant that can give up electrons and one that can receive electrons. And the reactant that can receive the electrons must want electrons more than the reactant that currently has the electrons. To simplify, in order for a reaction to proceed, the species being reduced must be higher on the table than the species being oxidized. And to further simplify, and I would add this to my data table, if we look up our reactants and we find that two reactants line up like this, then the reaction's a go. But if they line up directly over top of one another or diagonally in the opposite direction, then it's a no. The reaction will not take place. Examples. Which of the following combinations would yield a spontaneous reaction? We're starting with Br2 and Pb2+. I'm going to have to locate them on my standard reduction potential table and determine, according to their location, whether or not I have a spontaneous reaction or whether or not they'll do nothing. Pause now. Look them up. When you have an answer, then unpause the video. Welcome back. So you found Br2, it's over here, and Pb2+ over here. That's the only place they are located. They are directly over top of one another. They are not in a will position, so that means the reaction is not spontaneous. Good job. Now for B. Cu2+ and Br-. Look them up, pause the video. Once you determine whether or not it is spontaneous, then unpause the video. Welcome back. You found Cu2+ here and here, and Br- over here. Now it doesn't matter which Br minus we line up to the copper, it is going to line up in the won't position. So that means the reaction is not spontaneous. C, hydrochloric acid and magnesium. Look them up on your standard reduction potential table and determine whether or not it is spontaneous. Once you've determined that, unpause the video. Welcome back. Now, I'm sure you looked at HCl and you said that's a strong acid. And we know that strong acids dissociate 100%. So I actually have three things here. I have H plus Cl minus and Mg. Oh, so H plus is right here. Like I know it's all over the table, but I picked this line because H plus reacts with 2 electrons. And that's something H plus can do. I obviously can't pick the H plus up at the top because it says eight H pluses plus MnO4 minus, and I definitely don't have MnO4 minus. All the other H pluses have something that I don't have in this reaction. So this is the H plus I'm looking at. I also have Cl minus, which is over here, and I have Mg. Oh, Mg, there it is. All right, now, would a reaction take place? Well, it appears as though amongst those three things out there, the Cl minus won't be doing anything. It will just be hanging out in solution, but that H plus and Mg will react. So this reaction would be spontaneous. And you may recall from Physical Science 20, you did this reaction. The H plus reacted with the magnesium, producing hydrogen gas. We had stuck a little piece of magnesium in hydrochloric acid, it bubbled, we held a flaming splint over top of the test tube, it made a popping sound because the hydrogen gas that was being produced ignited. So we know, beyond a fact, from personal experience in grade 11, this is a spontaneous reaction. Not all half reactions are neatly located on your table of half reactions. This requires you to write the missing half reactions from scratch. This is accomplished by following these simple rules. Rules to balancing half reactions. Rule number 1. Write the skeleton half reaction from the information given. Rule number 2. Balance atoms with the exception of hydrogen and oxygen. Rule number 3. Balance oxygen by adding H2O to the side that needs more oxygen. Rule number 4. Balance hydrogen by adding H plus to the side that needs more hydrogen. Rule number 5. Balance charge by adding electrons to the more positive side. You would stop there if it says acidic or nothing at all. But if it says basic, you will continue on to rule number 6. If you are told it is basic solution, add an equivalent amount of OH minus ions to both sides as H plus ions presently found in the equation. Rule number 7, eliminate duplicate H2O on both sides of the equation. I know that's a lot, but we're going to practice it a lot, and it's going to become like second nature. And when we go through the examples, I'll go through that a whole lot slower. But these are the rules to balancing our half reactions. So let's do some examples. Example 1. Write the balanced half reaction for the reduction of NO to N2O. So first, write the skeleton half reaction from the information given. And we are told that NO is turning into N2O. Step 2. Balance atoms with the exception of hydrogen and oxygen. So that means we are going to have to balance nitrogen. So I have 2 nitrogens on the right, so I'll put a 2 in front of the NO, so that gives me 2 nitrogens on the left. Step 3, balance oxygen by adding H2O to the side that needs more oxygen. While the left has 2 oxygens, the right only has 1. So the right-hand side needs 1 more oxygen, so I add 1 H2O. Now the oxygens are balanced. Fourth step, balance hydrogen by adding H plus to the side that needs more hydrogen. While the right has 2 hydrogens and the left has none. So that means I need 2 more hydrogens on the left, so I add H plus to balance out the hydrogen. Now both sides have 2 hydrogens. Balance charge by adding electrons to the more positive side. On the left-hand side, I have 2 H pluses, which give me a +2 charge on the left. On the right-hand side, nothing has a charge, so there's a charge of 0 on the right-hand side. So I add electrons to the side that's more positive. I will add 2 electrons to the left to bring its charge then to 0, so it will match the charge on the right-hand side. And that's my balanced half reaction because it didn't tell me to continue on to basic. So, complete. Example 2, write the balanced half reaction for the oxidation of chlorine to chlorine trioxide in basic solution. So step 1, write the skeleton half reaction from the information given. Cl2 is turning into ClO3. Step 2, balance atoms with the exception of hydrogen and oxygen. So that means I am balancing out the chlorine. So I will need a 2 on the right-hand side so that I have 2 Cl's on either side of the equation. Step 3, balance oxygen by adding H2O to the side that needs more oxygen. I have 6 oxygens on the right-hand side, so I will need 6 H2Os on the left-hand side. Step 4, balance hydrogen by adding H plus to the side that needs more hydrogen. I have 12 H's on the left, none on the right, so I will have to add 12 H pluses to the right-hand side, so I have 12 hydrogens on either side of the equation. Step 5, balance charge by adding electrons to the more positive side. Right now I have no charge on the left, I have a plus 12 charge on the right. I always add electrons to the more positive side to balance out charge. So the right-hand side will require 12 electrons, and that will bring its charge to 0, and then it will match the other side of the equation. Now, typically, we would be done here, but the question says, write the balanced half reaction in basic solution. So we have to do the final 6th and 7th steps. If you are told it is in basic solution, add an equivalent amount of OH minus ions to both sides as H plus ions presently found in the equation. So I have to add as many OH minuses as I have H pluses right now. Now this equation is balanced, so whatever I do to one side, I do to the other. So since I have 12 H pluses, I will add 12 OH minuses to either side, and 12 H pluses and 12 OH minuses will make 12 waters, because an H plus and an OH minus come together to make water. So 12 H pluses and 12 OH minuses will make 12 waters. And that will bring us to our final step, eliminate duplicate water molecules on both sides of the equation. I have 6 water molecules on the left, I have 12 on the right. That means I can get rid of 6 water molecules on both sides. So that means the 6 on the left will disappear, and I will take 6 away from the right-hand side, which means I go from 12 water molecules down to 6 water molecules. All that's left to do is to write down what remains, which is 12 hydroxides plus a chlorine, turn into 2 ClO3s plus 6. Example 3. Write the balanced half reaction when P4 is converted to phosphate ion in basic solution. Identify as reduction or oxidation. So write the skeleton half reaction from the information given. P4 is turning into phosphate ion. Step 2. Balance atoms with the exception of hydrogen and oxygen. So I will have to balance out my P's. I've got 4 P's on the left, I'll need 4 P's on the right. Third step, balance oxygen by adding H2O to the side that needs more oxygen. Right now I have 16 oxygens on the right, so I will put 16 waters on the left so that I have 16 O's on either side of the equation. Fourth, balance hydrogen by adding H plus to the side that needs more hydrogen. Right now I have 32 H's on the left and none on the right, so to balance out hydrogens, I will put 32 H pluses on the right-hand side. Now I have to balance charge by adding electrons to the more positive side. Right now I have no charge on the left, but I have a plus 20 on the right. Plus 20 That comes from the fact I have 4 negative 3's, which give me a minus 12, and I have 32 plus 1's, which gives me a plus 32. And when I put together minus 12 and positive 32, that gives me a total of plus 20. So to make the charge balance out, I will have to add 20 electrons to the right-hand side, and that will make the charge on either side of the equation equal. Now, what are we going to do? I guess it says basic solution, so we got to continue. So if you are told it is in basic solution, we have to get rid of the H pluses, because H pluses are acids, and we are told it's in basic solution, so we have to get rid of the acids. And we do that by adding the same amount of OH minus ions to both sides of the equation that we currently have H pluses on, well, one side of the equation. So if I've got 32 H pluses, I'm going to add 32 OH minuses to both sides. Why both sides? Because the equation is already balanced. And whatever I do to one side, I'll have to do to the other. And we know that an H plus and an OH minus come together to make water. So 32 H pluses coming together with 32 OH minuses will make 32 water molecules. And that brings us to the last step. Eliminate duplicate waters on both sides of the equation. So I've got 16 on the left, 32 on the right. That means I can get rid of 16 waters on either side of the equation. So that will take out the 16 waters in total on the left-hand side. And when I take 16 away from the right-hand side, that is going to leave 16. 32 water molecules subtract 16 water molecules, leaves me with 16 water molecules. And then I just write everything that remains. 32 hydroxide ions plus P4 gives me 4 phosphate ions, 16 water molecules, and 20 electrons. Last thing, it said identify as reduction or oxidation. The electrons are on the right-hand side, which means they are leaving, so we're losing electrons. And if we lose electrons, it's oxidized, that's Leo. And that's the end of the lesson. You're good to move on to the RO6, 7, 8, 9 assignments.